Yes, hello, thank you very much. It's a pleasure to be here. I'm sad my co-authors couldn't be here to talk about all the hard work they did. I'll try to do it justice. All right, so we heard about the fact that JIT compilers are hard to write, and I will tell you more. They're also incredibly wasteful. So, if you think about what a JIT does, is it starts running, it compiles your code with some guess of what it will do, and then when the guess is wrong, it'll compile it again, maybe slightly differently, and so on and so on. So imagine that you have a library function. It may be recompiled a bunch of times during a run. Yeah. But now think about over the lifetime of your laptop. That library function, say some list concatenation, how many times are we going to recompile that same library function in different programs, in the same program, when you stop the VM, restart? Basically, you're going to waste so many cycles, which is a shame, right? All right, so in this talk, I will use a compiler that we've written. It's called sh, after me, sh. It's the R with the little thing. And it's a compiler for a statistical computing language. Doesn't really matter too much. And I will use it as an example. Other compilers are probably similar. So what do we do? When we start running, you load source code. Then you get bytecode, and this is done for us. So we have, that question, AST versus bytecode, has been taken off our hand. We get bytecode. And then what do? Well, we do some optimizations. We have our own IR. Then we translate it to LLVM bitcode. Then we call LLVM. Then it runs native. And if we realize that we made a mistake in our optimization, we're a bit too eager, we will de-optimize, go back to the bytecode, restart again. So that's the loop. So our goal in this work is to avoid all of these yellow, repeating the work on these yellow edges. And for this, we built an experimental version of sh. Let's call it sh plus. And basically what it does is you run the system first in a record mode where it does what it does, but it also records every compilation. It records some metadata and what bitcode you generated, and sends the code to a repository. And within the repository, we do some curation, get rid of duplicates, and so on. We can also do more optimization because we have time. And eventually, you will run again. And when you run again in replay mode, and you find out that there is a request to compile something, and the context, the environment, the stars are aligned, and you can find code in the repository, you will load it, patch it, and off you go. What we can also do is we can run in JIT-less mode, that is, which you can turn off the JIT entirely and run with an interpreter and with a compiled code base. Okay, so that's essentially the paper in a slide. We're on a tight time budget, so I'm speeding up. How does it work? I'll give you two bits of results. So the first one is, this is a benchmark, a computational benchmark. We're showing performance with our sh classic and our sh plus. So green is plus, lower is better. Every dot represents one run of the same program with the same input in the same VM. So you fire up the VM and you just repeatedly run this stupid program, and we measure performance. We are running with the code repository that has been built before, so we're not measuring that. But what we can see is the difference between the green and red are speedups. And they're typically due to fewer compilations. So every time you see these, you say, I'm saving a little bit of time. The savings are greatest at the beginning because Sh classic has no cache, so it has to compile everything, and eventually things go pretty much the same speed. The differences are statistical noise. Here's another experiment, which is interesting to me. So we picked a well-known package in the ecosystem we are in, and we checked out 6 versions of the same package over a span of a year. And then we ran the system, built our code repository on the first version, and froze the repository and kept it same. And then ran the test suite with different code bases. So the idea is, so the first bar you see is the time it takes to, the speed up we get on the 0th iteration, and the axis are seconds. So it's a lot of time because every one of those tests, and there are lots of tests, fires up a new VM, which has to start everything from scratch, compile the same code again and again. So test suites are really expensive in our world. So we can sort of cut down the compilation cost. Now, the other bit that is interesting is, if you look just at the green dot, is this sort of slow trend up. It's what I call decay, because we captured code, the first version, and over time, we're sort of running different code bases. So there are some things we can reuse, and some things that have changed, or the context is different, so we realize, no, we can't reuse the optimized code we had. And in those cases, we have to compile. And the good thing is the decay is fairly small. All right, so these are our results. We're happy with them. The paper is done, or my job is done. I will leave you with one thought. What is the research part? It was a lot of engineering, it was hard. But there's an interesting research question. So, as I told you in this last experiment, we're trying to reuse code that was compiled in another run of the VM. Well, it's really code that was compiled for another program. So I have 2 programs with whatever changes you want. When is it safe to take a piece of code that was jitted in one context and reuse it in another context? That's the interesting question. And for that, I will tell you how to build a JIT and answer the question whether it is actually hard. So, how do we build a JIT? Well, the first thing we need to do is speculate. So here's a bit of old work we did. So we have a program on the left, and it's doing some arithmetic computation. And let's just say this is our base version of the code the compiler generates. It's not particularly interesting. It's unoptimized. It does whatever the source program did. Okay. Then the way these things work is the compiler runs for a while, gathers some profile, and at some point comes up with a guess. And here our guess is going to say, well, I'm guessing you want to call this function fun with arguments z of value 7 and x of value 75. It's my guess. I have the right to do this. And if that is true, then I can optimize the code to be this trivial little bit. So what does the JIT do? It does 2 things. It introduces two instructions, assume, which is saying, these are the facts I'm assuming for correctness. If they do not hold, then there's the anchor, which says, jump to the anchor and de-optimize. So if my assumption here does not hold, I will jump to the anchor statement. The anchor statement says, so we want to de-optimize. So what you need to do is call the function base, jump to label 1, recreate the stack with your current values of x, y, and z, and add a local variable d, set it to 1. That's what a JIT does. So no harder than that. Assumes, anchors, you know how to build a JIT. The problem with this is de-optimization, wasteful. So what if we wanted to avoid the optimization? So then we did some work on that, and the idea is, well, every time you have one of these assumes, this is a likelihood your code will de-optimize. So this was my optimized function. What if I could move some of these assumes out of the code of the function and make them like preconditions. So here I'm showing I'm lifting that assume out of the body and say, let's just say it has to be true. Then if I can do that, I can get rid of my anchor and the code will never de-optimize. So now the game is, we can say, if there's a way for us to move some of these assumptions out, we can get the guarantee that there'll be fewer opportunities for the optimizations. So imagine here a function that reads a global variable and calls the dynamic plus method to add it to its argument. So what we do in our compiler is we will say, let's compile a version of this function with the precondition that the argument is an int. And now, inside of the body, we don't have to check. We know that this is going to hold. We can make other assumptions. So here we're going to assume that the global variable holds an int and that plus hasn't been redefined. They're useful assumptions. So it can still de-optimize, but some of the problems have been lifted out. And so on, you can generate various versions. So version 2 assumes the argument is a string. Version 3 says, well, it could be a string or an int, I don't know. And each of them makes optimizations. So then what do we do at runtime? Well, when we see a call to the function, we will have to pick which of all the versions we have we're going to jump to. And that we do by building a context and dispatching on the most applicable context. All right, so this is old work. So what is the new bit? So the new bit is to allow us to reuse code, we want to increase the information content of this context with what we call speculative contests. And the idea is, with speculative context, we'll be able to reuse code across different programs and different execution environments. So our context was the type of the argument. I mean, you can have many other things, but for this example, we use that. Now, and that's our K, the context, and now we are going to expand this with S, which we call the speculation, and essentially it is what does the JIT speculate on in the body of this method? So K has to hold. If you don't have K, if it's not correct, your code will crash. S is the set of things I'm going to check on which I may or may not de-optimize. So now to answer the question I started with, when is it sound to reuse compiled code? Assume I had a piece of code that I compiled with the expectation that the type of the function could be an int or a string, and that it's going to de-opt on an int. And now I'm calling it, and I know that the argument is int. So is it safe? Yes, because the code was compiled in a more general context than the type you have at the call site. So essentially, you want a relation on context such that you can say this context is more precise than that one. And if you have a more precise context at a call site than the code you generalized, you can safely jump into the code. What about the speculations? Well, speculations actually don't matter because the speculations are going to be dynamically checked. So even if they're completely different, you would be fine. But in practice, since we don't want to de-optimize, we're going to say, try to pick the speculations that are the closest between all the set of methods you have. So, how much time do I have? 2? 4? Okay, all right. So, example how this works. So, remember I had this function that was reading a global variable and then adding it to its argument. So let's see how this would work in our system. So you set glob to 42, and you start running the function. The function will run in the interpreter. It will gather profiling data. Then eventually, you call it again. Now you have profiling data, and when you're calling it, you have a context. You know that you're calling it with an int. So you can query your database and say, do you have some compiled code for this function that runs in context int and speculates on int? And it so happens that we have v1 that we showed earlier. So we get v1 and we start running optimize. The next time we call fun, we're changing the type of the argument we called with a string. So now you're going to jump out of this code. You can't use it. We're going to go back to the interpreter, going to observe, get some feedback. And then when you call it again with a string, you can say, well, now I'm calling you with a string and my feedback is that my global variable is an int. Do you have a version compatible? Yes, I have v2. Now you run fast. Next thing is the programmer changed the number 42 to a string 1. This will cause the optimization because we have an assume in there that was assuming an int. And then eventually we will get to run native code again. So this is the general idea of what we're doing. So to sum up is we have this notion of entailment over this context, and that's the key to reuse code across programs. And different languages can do it differently. You can have more information in those contexts. One last thing I want to tell you is what we found is, so here you see two contexts that are different and the same code. What we found is often you get a compilation request with a different environment, but the code is exactly the same. How often? About half of the time. So half of the pieces of code we compile and then end up being bit for bit equivalent. So what we do is, well, we curate them. We just throw away the ones that are equivalent. We keep the more general context. But one could be more smart about this and say, well, even if they're not equivalent, is the difference between the two versions worth having compiled code in your database? Or is it just rearranging, some small unprofitable computations? So we're not doing that, but that would be cool to do. So to conclude, you can reuse jitted code, and that will reduce your warm-up time. And the key idea here is and what makes our work different from previous work is we keep many, many versions of a function, and we find the most applicable version for the context in which you're running. Thank you very much.
Very interesting work, thank you. I was wondering if there's any potential security considerations to account for if you're writing out information about what branches are taking potentially in your code and that's being used in other processes. Is that something you've thought about at all?
Oh, yes. So I mean, the sort of the simple answer is if you worry, you can have the code cache be user, sort of specific to a user. If you don't worry, you can share it across, the whole organization. But clearly, anytime you record anything about an execution, you're leaking information. And then the question is this information actual security risk? Is for better people than me to decide.
Yes.
Okay, thank you, Jan.